Okay, in this video, we're going to be doing part 4, I guess, of assignment number 5 from my Calc CD class. We're evaluating the double integral over R, which is a region in the xy plane, of f of xy dA, which kind of means we get to pick our own order. And then R is going to be a rectangle in this case. So we're going to go from A to B for x and then from C to D for y. So let's dig into these problems. So double integral over R of x over y dA. R is -2 to 4, so those are x values, and then 1 to 3, those are y values. So the first thing I'm going to do is I'm going to just write the double integral with the bounds put in. I'm going to go, anytime I have a choice, I'm going to do dy and then dx, because in my mind it makes the most sense to do dx last, because most of the integrals I've ever done in my life finish off with like dx. So that's kind of my thought process there. So I set it up like this. We're going -2 to 4. 1 to 3, x over y dy, so we'll do that integral, and then dx. But then we notice that x over y is really just the function x times the function 1 over y, so we can use that property where we're going to split this into two integrals, get them, and then multiply the result. So what I mean by that is my next step will be to rewrite this thing as -2 to 4 of x dx and 1 to 3 of 1 over y dy. I can do that because the integrand is a product of a function of x and a function of y. Otherwise, you can't do it. You have to do it a piece at a time. All right, so then fundamental theorem, both of these things. So this will give us 1/2 x squared from -2 to 4. This next one will give us the natural log of the absolute value of y from 1 to 3. Fundamental theorem, right? So we plug in 4, plug in -2. So it'll be 1/2 of 16 minus 4 times, got to use parentheses to make sure everything distributes correctly. It'll be the natural log of 3 minus the natural log of 1. Natural log of 1 is 0. So we get 16 minus 4 is 12, over 2 is 6, natural log of 3. And that's our answer. So these aren't really that bad. They're like set them up and do them type problems. But let's keep going. So we're gonna do all of them anyway. So double integral over r, x squared times y. Again, we make the observation that x squared times y is f of x times g of y. So we're going to be able to turn this into a product of integrals that we would have done in like Calc 1. And then dA, where r is the region from -1 to 1 for x and 0 to 2 for y. So again, I'm going to set it up the way that I always do. I like to do dy dx. That's my preference. If I can't do that, then I'll do dx dy. But the only way that could be forced is if we're not integrating over a rectangle, which we'll see soon in probably the next assignment. So -1 to 1, 0 to 2, x squared y dy dx. Break it up into two things. Well, break it up into a product of integrals. So -1 to 1 of x squared dx, 0 to 2 of y dy. It's helpful that I'm color coding it. I don't think in the real world I probably wouldn't do that. It'd be too annoying to pick up different pens. It was very annoying to make the video, in fact. So I hope someone out there is appreciating this. All right, so two Calc 1 level integrals here. So we'll reverse the power rule. 1/3 x cubed from -1 to 1. And then we will reverse the power rule on this. We'll get 1/2 y squared from 0 to 2. Fundamental theorem for both. So we get 1/3, and then you have 1 minus -1, right? Because -1 cubed is -1. And then you'll have 1/2 4 minus 0. And then we just clean this up. This will ultimately give us 2/3 times 2, so 4/3. All right, let's look at the next one. Double integral over r cosine x sine of 2y dA. R is from 0 to pi over 2. Those are x values. And then 0 to pi over 2. Those are y values, although I guess in this case it wouldn't have mattered. But it does matter. It's always x and then y. And then if there's a third one, it'll be z. They're always in that order to avoid confusion. All right, so set up our integral. And again, I'm going to go dy dx. So 0 to pi over 2, 0 to pi over 2, cosine of x, sine of 2y dy dx. This, again, is a product of a function of x times a function of y, so we can turn this into a product of integrals. I use that property every single time I can. I mean, I know that these are double integrals, but it's so much easier to do single variable integrals, so I will always change them into that if possible. It's not always possible, but on these it is. All right, so antiderivative of cosine is sine from 0 to pi over 2. Antiderivative of sine of 2y is going to be -1/2 cosine of 2y. So don't forget that negative, and then we're going from 0 to pi over 2. We plug in, so I showed it's sine of pi over 2 minus sine of 0. We have to remember some values here, and then negative cosine of pi plus, because it's minus negative, so plus 1/2 cosine of 0. Sine of pi over 2 is 1. Sine of 0 is 0. Cosine of pi is -1. cosine of 0 is positive 1. So with all of those in mind, we just end up here with 1 times 1/2 plus 1/2. So that's 1 times 1, which is 1. All right, let's look at the next one. I know I'm going kind of quickly, but you can always slow it down or pause or hopefully work these out on your own and then just be comparing. Let's look at the next one. Double integral over r, y over x plus 1. So again, it's the function y times the function 1 over x plus 1. That's a function of y times a function of x. It's always, you gotta like keep that in mind and make sure it's true. So dA and then r is 0 to 2, 0 to 4. So x's go from 0 to 2, y's go from 0 to 4. Set up your integral. We have this. I'm going to take advantage of the fact that it's f of x times g of y and split this into a product of two single variable integrals. So we have 0 to 2 of 1 over x plus 1. That's a natural log. And then 0 to 4 of y, which is going to be reversing the power rule. So let's actually do that. So this will give us the natural log of the absolute value of x plus 1 from 0 to 2. And then 1/2 y squared from 0 to 4. We plug in, so natural log of 3 minus natural log of 1. And then we plug in, we get 1/2 the quantity 16 minus 0, which is 1/2 of 16. The natural log of 1 is 0. You really need to remember that. It's important. It comes up a lot. So this will be the natural log of 3 times 8. There we go. All right, we got a couple more. 3, maybe 4 more. All right. Double integral over r e to the x times sine of the y, sine of y dA. R goes from 0 to 2, 0 to pi over 4. Set it up, and then split it because you can, right? F of x times g of y. That property is amazing. And it keeps coming up like forever. Like it's not like it just totally goes away. You will almost always be able to use this at some point in any given problem set. Not definitely, but you know, be on the lookout for it. All right, integral of e to the x is e to the x, and we're going from 0 to 2. The integral of sine is negative cosine, and we're going from 0 to pi over 4. Again, we're going to have to remember some values, but let's use the fundamental theorem. So e to the second minus e to the 0, and then negative cosine of pi over 4 minus negative, so plus cosine of 0. Cosine of pi over 4 is root 2 over 2, and the cosine of 0 is 1. So that's going to give us e squared minus 1 times negative root 2 over 2 plus 1, but I'm going to write that as 1 minus root 2 over 2, because I think that makes more sense, but, you know, it's not mandatory. They're numerically equivalent. All right, next up, number 42, double integral over r e to the 3x plus 4y dA. R goes from 0 to 1 and then 1 to 2. So initially you might be thinking like, ooh, we can't use that property, but we can because e to the 3x plus 4y is the same as e to the 3x times e to the 4y. So it is a product of a function of x and a function of y. So I'm going to start off by just writing my double integral like so, and then I'm going to split it and just multiply the results. So we get this 0 to 1 e to the 3x dx times 1 to 2 e to the 4y dy. So use substitution or reversing the chain rule, however you like to think about this. The antiderivative of e to the 3x is going to be 1/3 e to the 3x, and we're going from 0 to 1. And then the antiderivative of e to the 4y is going to be 1/4 e to the 4y, and we're going from 1 to 2. Plug in, I don't think there's going to be a lot of simplifying here. So we get 1/3 e to the 3rd minus e to the 0, which is 1. And then we'll have 1/4 e to the 8th minus e to the 4th. I don't want to multiply those, so I'm just going to write my answer as 1/12 e to the 3rd minus 1 e to the 8th minus e to the 4th. Even saying it is kind of not great. I think that's as good as it's going to get. Like, I mean, you could multiply that out. I don't know. Probably like an answer key might multiply that out. But again, like, do I know what that is? It's huge. That's an enormous number, but I don't know what number that is. All right. 43. This one's a little bit different, but really not that much. So f of xy is m times xy squared. We want to find m so that the double integral over r of f of xy dA is equal to 1. So it just has like this little thing at the end where we have to solve. R goes from 0 to 1 and 0 to 2. All right, so let's set up our integral. So I'm going to pull out m. It's a constant multiple, right? So m, 0 to 1, 0 to 2, x, y squared, dy, dx. Fine. This is a function of x times a function of y, so I'm going to make it a product of those single variable integrals. And my goal is kind of always to go back to doing Calc 1, I guess you might say. So 0 to 1 of x dx, 0 to 2 of y squared dy. And all that should equal 1. All right, so it's going to be m, and then 1 half x squared from 0 to 1, 1/3 y cubed from 0 to 2, and again, it just equals 1. We apply the fundamental theorem. This is going to give us, because the lower bounds are both 0, it's like you just plug 1 into the first thing and 2 into the second thing, so we're going to get m, and then 1 half there, and then 8/3 here, and that should equal 1. And so solve for m, and we get 3/4, and I think that that is the entire problem set. So that is the end of the 5th assignment. I hope this was helpful, and good luck.